In this video, we're going to talk about exponential functions. So an exponential function is a function of the form f of x equals b to the power x, where b is greater than 0 and b is not equal to 1. So again, you choose b. If b were equal to 1, that would just be 1 to the x, and that'd just be the function 1, f of x equals 1. So ignore b equal to 1. Now, the domain of this function is a set of real numbers. You can plug any number in for x. And the range is the set of positive real numbers. So this function is always positive. B is called the base, and x is called the exponent. There's some features of this function. First, all graphs pass through the point 0, 1. If we look at our function, b to the power 0 is always 1. All graphs are continuous. The x-axis is a horizontal asymptote, and we'll see that in a minute. If b is greater than 1, then b to the x increases as x increases. And if 0 is less than b is less than 1, then b to the x decreases as x increases. So here are a couple pictures. So on the left, b to the x for b greater than 1, and you can see the function increasing as x gets bigger. And you can see the function tend towards 0 as x becomes large and negative. And then b to the x on the right for 0 less than b is less than 1. As x gets large and negative, the function gets very big. And as x gets large and positive, then b to the x tends towards 0. And that's your horizontal asymptote. There are lots of properties of exponentials that you need to know. Okay, so we've got a and b positive, b is not equal to 1, and x and y are real numbers. So if we have a to the power x times a to the power y equals a to the x plus y. So basically you add exponents. A to the x divided by a to the y is equal to a to the x minus y. And that just follows from the previous one, because a to the x divided by a to the y is equal to a to the x times a to the negative y, which of course is just a to the x minus y. A to the x to the y is a to the xy. So if we take something like 2 to the power 4 squared, that's equal to 2 to the 8th. AB to the power x is equal to a to the x times b to the x. So 2 times 3 squared equals 2 squared times 3 squared. A to the x equals a to the y if and only if x equals y. So 3 to the x equals 3 to the y is only true if x equals y. And for x not equal to 0, a to the x equals b to the x if and only if a equals b. So of course, if x equals 0, then this is just 1 equals 1. So that's always true. But a squared equals b squared is only true if a equals b. Okay, some exercises. 2 to the power 3x minus 5 equals 2 to the 4x minus 2. Now that's only true if 3x minus 5 equals 4x minus 2. And now we do a little bit of algebra here. That's going to be negative 3 equals x. I took the 3x to the right. I brought the 2 to the left. Negative 3 equals x. Let's just check that. 2. Negative 9 minus 5 is negative 14. 4 times negative 3 is negative 12 minus 2, negative 14. 3 to the x squared equals 9 to the x. So this takes a little bit of work. We've got 3 to the x squared equals 9 is 3 squared to the x. So 3 to the x squared, again, if we take something 3 to the a to the b, we multiply exponents. So that's 3 to the 2x. This is only true, we're back to the original problem. If x squared equals 2x, x squared minus 2x equals 0. factoring x times x minus 2 equals 0. So x equals 0 or x equals 2. And let's just check here. So we're doing 3 to the power 4, for example, equals 9 to the power 2. That seems correct. And if we put in 0, we get 3 to the 0 equals 9 to the 0, and that's certainly true as well. 3x plus 5 to the power 4 equals 10x to the 4th. Okay, so if we had the same exponent everywhere, these would be straightforward. So what we need to do is rewrite this 10 so it's something to the power 4th. So 3x plus 5 to the 4th equals, I'm going to take the 4th root of 10 to the power 4 times x to the power 4. And now we can use our properties of exponentials. Again, if we're multiplying two things both to the power 4, we can multiply the things inside and to the power 4. So that's going to be the 4th root of 10 times x to the power 4. If we have two things to the same exponent, then they must be equal. The terms inside must be equal. 3x plus 5 equals the 4th root of 10 times x. Okay, so now we'll bring the x's all on one side, the 5 to the other. So that's going to be 3 minus the 4th root of 10 x equals negative 5, which implies x equals negative 5 divided by 3 minus the 4th root of 10. Okay, that was a little complicated. Now we've got x squared e to the minus x plus 3x e to the minus x plus e to the minus x equals 0. Let's factor out that e to the minus x. X squared plus 3x plus 1 e to the minus x equals 0. Now, if we're multiplying two things together and they equal 0, one of them must be 0. Well, e to the minus x is never 0, so it must mean this term is 0. So we have x squared plus 3x plus 1 equal to 0. And we need to factor this. Well, I look at it for a second and I go, I don't know what those factors are going to be, so I'm going to use the quadratic formula. So x equals negative b, negative 3, plus or minus the square root b squared, which is 9, minus 4ac, which is just 4, all over 2a, which is 2 times 1. So that's negative 3 halves plus or minus the square root of 5 over 2. So again, look at your quadratic equation for a second. If you can't see the factors, pull out the quadratic formula. Negative 3 halves plus or minus the square root of 5 over 2. Okay, so this is just some simple manipulations of exponentials. The expectation is these are relatively straightforward. They may take a little bit of remembering. Okay, now we want to talk about the base e. So e is this number, 2.71828183, and so on. So it's just this number. And e to the x is our most useful exponential function. E can be approximated as 1 plus 1 over x to the power x. If we put in large numbers for x, we'll see that that works. And one of the places you're going to see e to the x is in interest calculations. So when doing interest calculations, and in fact for me, I never did the interest calculations you've probably seen and used before have been these, right? You have principal P, it's invested at an annual rate R, compounded M times per year. Then the amount A, the future value in the account at the end of T years, is P, 1 plus R over M to the power MT. And sometimes you'll see this P equals how much money do I have in the future? 1 plus R over M to the power negative MT. You'll see this. Sometimes P will be called the present value, A will be called the future value. And this is our compounding formula. And to be honest, I never use this. This is not a formula that I ever really use. I will use this formula with m equals 2 semi-annual interest for bonds. Right? This is how bonds are quoted. So I will use m equals 2 semi-annual for bonds. Now, the one that I like is continuously compounded. So if a principal P is invested at an annual rate R with continuously compounding, then the amount A, the future value, in the account at the end of 2 years is A equals P e to the RT. And again, we can rewrite that present value equals future value, or A, e to the minus RT. These are formulas that you're going to have to be comfortable with. Future value instead of A equals present value e to the RT. I grow using a positive power. I discount using a negative power. We're going to do this all the time. Okay, some exercises. We want to find the value of an investment of $20,000. So we're investing $20,000. We want to know what this is worth in 5 years if it earns an annual rate of 2% continuously compounded. So here, the future value is equal to $20,000 e to the R 0.02 times 5. Let's just pull up a calculator, find out what this is. I guess we don't want a standard calculator. Let's use scientific. So 20,000 times 0.02 times 5 is 0.1 e to the x 22,103.42 equals 22,103.42. Let's just check that I wrote that down correctly. 22,103.42. Now we can ask ourselves the question, what if this is semi-annually compounded? All right, so future value equals 20,000. 1 plus R 0.02 over 2, that's how often we compound, semi-annual is twice a year, to the 2 times 5. So that's equal to 20,000, let's put the commas in, times 1.01 to the power 10. All right, let's pull our calculator back up. 20,000 times 1.01, let's find our button, x to the y, 10, 22,092.44. 22,092.44. And if you notice, and as you probably already know, if you earn interest semi-annually compounded, you end up earning less interest at the same rate than you would with continuous compounding. 22,092.44 is less than 22,103.42. Now the reality, and we'll talk about this later in class, is that you're never given this choice, right? If this, the 2% continuously compounded, was fair, then you would earn a slightly higher rate of interest if it were semi-annually compounded, so that when you did this calculation, you ended up with the same amount of money, 22,103.42.